back to this class on hardware security. So, we shall be continuing our discussions on row hammer attacks. So, we have already kind of seen the background behind the attack, and today we shall be seeing the actual attack and also discuss a potential countermeasure. So, where we stopped in the last class, where we were basically determining the LLC slice where the secret maps. So, we saw how prime and probe can be utilized in this context. So, in particular, right, we already discussed that we basically, so the experimental setup that we are considering here is essentially an RSA implementation with 1024 bit exponent, which basically can reside in two cache lines, each of 64 bytes. So, you can see that totally it is 1024 bits. So, it can be organized, or it basically takes or occupies two cache lines where each of them are of 64 bytes, okay, 64 into 8 into 2. So then 11 bits of the physical addresses refer to the last level cache set, okay, and essentially gets your corresponding cache set in your and we are considering four cores. That means we have a mapping to get 4 cores, and there are 4 corresponding slices in the cache memory. So, the corresponding hash functions, which essentially has been reverse engineered in a prior work which I mentioned in the last class, essentially are shown by these two equations. So, you can see it is a simple linear equation which apparently gives you the corresponding mapping of from the physical address bits to 2 bits H0 and H1, through which you can basically index these 4 LLC cache slices. So, now previously, right, we had discussed about that we were basically doing an attack on, or trying to basically fix the corresponding cache set where there are mk possible values, right. For every slice there are m possible ways and there are k slices. So, putting the values here, m is 12 because the associativity that we considered is 12, and there are 4 slices. So, there are 12 into 4, 48 data elements. So, we basically the moment we fix a cache set, there are 48 possible addresses which we use to prime and probe. So, here is an experiment to show that it works. So, for example, you see that there are two graphs which has been shown over here. One which corresponds to a collision, for example, the blue which corresponds to a collision. That means the corresponding cache set which you are basically using to prime and probe is basically colliding with your secret exponent. And you can see that if there is a collision, then that means, right, that is essentially, so when the spy comes back and probes, it basically expects that there should be an increase in the average time, and that is what you can observe here. Since there is a collision, you find that the average cache access time has been increased, and therefore the spy is able to understand the correct cache set where the secret exponent is getting mapped to. So, the sets are chosen such that one of them is having a collision with the secret exponent and the other set does not have any collision. The average access time of these two sets during the probe phase, when you are coming and probing, you are seeing differentiating by approximately by 80 clock cycles. So, which shows that there is a significant discrepancy between these two timings, and which basically kind of leaks information about the LLC mapping of your secret exponent. But remember, right, at this point we basically have kind of still 12 into 8, 48 possible address locations, 12 into 4, 48 possible address locations. You can actually make this more concentrated by getting into the slice. So, you can use those two hash functions to basically also kind of get mapped into not only m into k, but get into one slice. So, that means in one slice for every cache set there are m possible ways. So, therefore, here is an example of when you are considering two slices. So, just to understand that whether you are correctly understanding the slice, for example. So, for example, in this case in figure A, the secret is mapped into LLC slice 0, while in figure B the secret gets mapped into LLC slice 2, and you can see that when it is essentially getting mapped into slice 0, then slice 0 is indeed taking more time corresponding to slice 2. Okay. Whereas in this case the secret gets mapped into the LLC slice 2, and therefore the probing phase indeed tells that the mapping for slice 2 is taking more time, and therefore you are correctly able to understand the slice, and that in a way says that the reverse engineering for the hash functions for the slice computations are working as expected. So, in both the figures, the access time for the cache slice where secret access collide is observed higher than the other slice belonging to the same set, but for no cache collision. So, that means, right, previously you had an ambiguity about the, like when you are considering, or in the previous case we had 4 slices. So, for a given cache set, right, we had all these things in my eviction set, and now if you can understand the slice also, then you have just m possible ambiguities. So, from mk you can reduce the ambiguity to m possible options. So, therefore, right, I mean what you can do is improve it. So, therefore, you can pinpoint the target LLC slice, and the adversary identifies the target LLC slice by iteratively running prime and probe protocol separately for each k slices with the selected m elements for that particular slice. The timing observations while probing will show significant variation for a set of m elements which corresponds to the same slice where the secret maps, and thus we further define the size of eviction set from m into k to only m possibilities. So, here is another alternative hash function which was presented in a following work, and if you use it, right, then apparently you can get a better separation. But so that means, right, you can actually use potentially few options, and essentially it works either or. So, essentially you can take any one of them as a possible representation of the corresponding mapping. So, now you have to basically get into the actual attack, but for the actual attack you also need to kind of determine the DRAM bank where the secret maps. So, the objective of the eviction determination was, for the cache set eviction detection, was basically to ensure that the decryption, when you are doing decryption, then you are basically accessing the DRAM, but now you have to do the actual row hammer, which means you have to basically ensure that when you start accessing again and again in a very repeated manner, then you basically access the bank where the secret essentially getting mapped to. So, now, in the first phase of the attack, you basically kind of restrict the attacker to go to the DRAM bank, but now you also have to go to the same DRAM bank and do the row hammering operation. So, you need to do this reverse engineering. So, therefore, in order to identify the target DRAM bank, so we will again use a prior result which is essentially shown in some of these equations, like from the physical address, how to get the bank number, how to get the rank number, and how to get the channel number. In particular, you see that this is the corresponding way of how to get the bank number. So, in our experiment, there are 2 channels, there is 1 DIMM per channel, there are 2 ranks per DIMM, and there are 8 banks per rank. So, we basically finally want to get into the bank, right, and since there are 8 banks, you can observe that number of bits which you have for the banks are 3, BA0, BA1 and BA2. So, therefore, if you know the physical address, you can calculate the value of BA0, BA1 and BA2, and you can calculate the corresponding bank numbers for those physical addresses. So, the objective is that the concurrent, so you want to basically inflict this row hammering or do the row hammering. So, you have to therefore concurrently access to basically what you want to do is you want to develop or do concurrent access to different rows in the same DRAM bank, and this will result in a row buffer conflict, as we have discussed. If you remember the old code that we discussed, when we basically were addressing x and y, we wanted to access different rows in the bank. The objective is we wanted to kind of evict the data from the row buffer, so that rather than accessing data from the row buffer, I access the data from the actual rows. So, this is called as a row buffer conflict, and this will automatically lead to higher access time, because if I get the data from the row buffer, that will take more time. So, we again use this timing difference to understand that whether we have been able to successfully evict the data from the row buffer, and we basically kind of access data from a different location in the bank, or different row in the bank. Now, the functions which decide the channel rank and bank map or bank mapping from the physical address are not disclosed typically, but as I said that we are use these equations which have been kind of published in some prior research works. And also, just to mention here that in a bank there are apparently something like 2 power of 14 rows. So, it is difficult for us, right, to get the exact row number in the bank. So, we basically do not have a handle to get into the row. So, we can basically get to the bank, but for like accessing or getting into the corresponding adjacent rows, we basically have to do repeated attempts and assume that few of them will be successful. So this is the complete elaboration of the attack. So in this elaboration, right, we see that there is an adversary which initiates the spy process, and as I said that you have to again decipher that eviction set. You have to do it every time in situ, because the mapping from the virtual address to the physical address will basically change when the moment you basically run a different process. So therefore you generate the memory map and you compute the set slice addressing from the physical addresses. You compute the channel, the rank, bank indices from the physical addresses, again by using the equations that we just now discussed. And then you basically calculate the eviction set C, and then you fill this or prime this with elements mapping to the same LLC set and slice as the secret. And the idea is that for each bank B in the DRAM, for each rank, bank, so basically as I said that you now from your physical address, which you have basically obtained by doing page map, you basically can calculate the corresponding bank number using the equations BA0, BA1 and BA2, okay, or BA0, BA1 and BA2. You can get the corresponding bank numbers. There are 8 possible banks. So you basically start targeting one of the banks, for example, say the bank 0. So in bank 0, if you target bank 0 in the DRAM, you basically prime the LLC by accessing these elements in the cache. So basically now you start that actual attack. So now after you have done this homework, the moment you start, you basically start your attack by fixing a corresponding bank number, say bank 0, and then you basically prime the last level cache by accessing elements in your eviction set. And then you basically the adversary or allow the adversary to, or the adversary basically sends or triggers the decryption, and note that since you already understood the eviction set previously, when the secret exponent runs, okay, since you are accessing in the same eviction set or in the same footprint of the cache memory, then that would imply that this location or this access has to be done from, you are basically trying to ensure that this essentially is not obtained from the cache, but is done from the actual DRAM. Okay. So therefore, right, you basically do the decryption runs. When the decryption runs, it is accessing these 2 lines as we have discussed, but this access is done not from cache but from DRAM, because this address space or this eviction set is conflicting with my spy. The spy has ensured that I have kind of evicted that area, that address from the cache, and therefore when the decryption is running or executing, that content is not available in the cache. So now when you basically come to, like when the moment the decryption after the decryption basically runs, so in parallel, right, or in conjunction, you basically access randomly selected data which basically maps to the target bank B, for example the bank 0, and you basically time your accesses. The objective is that now you know that the decryption is accessing a specific bank, and you want that as a spy, when you are accessing some locations, you are also interested to access in the same bank, okay. But you are also interested not to access the same row, but maybe some adjacent row, okay. So how do you know that? So the idea is that if you access the same row, then you would get the data from the same row buffer, and therefore, right, you will basically take less time. So that's why, right, you kind of time your access, because you can do that as a spy, you can time your own access, and you assume that if there is a more time requirement, then you basically are getting the data from the row buffer, but what you want is, or what you are interested is in the accesses which essentially takes more time, because that essentially is implying that you are accessing in adjacent rows. So and also, right, you after you do this access, every time you apply, you would like to flush, or because the moment you make an access, the data comes to the cache, and you do not want to access the cache because you are interested now to go into the DRAM. So you apply a specific instruction which is called CL flush to ensure that this data is evicted from the cache, and again, right, when you do that access, you are again accessing into the actual DRAM bank and not the cache memory. And finally, right, you get the decrypted message from the decryption engine, and this process is repeated again and again until and unless you are able to create the fault. okay, or the error. So, after repeated runs, for example, this snapshot says that it took some amount of time, but you can see that there is an error which has been reported in a specific bank. For example, this has been found in bank 7, where there is a bit flip. For example, initially everything was all F's, that means the entire content was all 1, but suddenly there is a bit flip for which this F has become E. So, we know that if you are able to create one single flip, then that essentially has got significant consequences in the security of crypto systems, whether it is AES or whether it is RSA or whether it is any other crypto system, and therefore, right, this flip, right, can be potentially exploited in doing or launching a fault attack, for example. So, here is, for example, a distribution of bit flips that was obtained in our experiments. So, we have got like from 0 to several banks that we have, these are the bank indices, and you can see that this is, for example, quotes the number of bit flips. So, you can see that some of the banks are not really prone to this kind of flips, but some of the banks are really prone to such kind of bit flips, where the incidence of bit flips is more probable compared to the other. So, this is an interesting statistics that which can be observed. So, if you discuss about the attack, so this attack essentially shows that it basically assumes that the secret decryption exponent resides in a particular location of the DRAM and is not page swapped by other running process. I mean, that is not removed away to the disk, for example. And so, you can basically, this seems to be a quite practical assumption in several settings, and the access to the page map, as I said, is not available at user privilege, but still in several scenarios you may still find that this is enabled, and there may be other ways of getting handle on the physical address as well, and also maybe in some other settings, right. For example, in a cross VM environment, right, I mean, where the users of the co-located VMs actually have administrator privilege, you can potentially still use this page map and can still try to sort of conceptualize an attack. And the attack in its original form might be relevant in customized embedded system applications where such threats can still be prevalent. So, how do you counter these attacks? So, one of the very popular techniques for preventing this is published in this work and essentially called as anvil. The idea of this anvil is that it resides in the kernel, and this basically is a kind of a good usage of performance counters, which we have already seen how we can perform. As I said, we can use hardware performance counters as exploits, but it can also be used for evaluations. It can be used for protections against side channels or side channel attacks. So, for example, performance counters have got are available on Intel Sandy Bridge and later microarchitectures, which can be utilized. So, the idea behind this strategy is as illustrated here. So, you basically you monitor the LLC miss rate and try to see that if the miss rate is high enough. Okay. So, you basically monitor the last level cache miss count, and then you basically sample the LLC miss addresses and see that whether the misses have got high row and bank locality. Okay. So, you can do that, you can sample the misses out of your LLC, and then what you do is you basically, the moment you basically have a suspect of this, you kind of selectively refresh the rows, and that would kind of thwart the basic idea behind row hammers, because the row hammers basically, or the row hammer bug works because our access is faster than the refresh cycle. So, if we can refresh it, then it will not work, okay, and therefore, we can protect against the attack. So, to conclude our discussions overall, microarchitectural attacks encompass the intersection of architectures and computer security. So, we have seen several things, and for example, we have seen the effect of cache memories, branch predictions. We did not discuss in details about prefetchers and speculative executions, but this also has got a significant impact on the overall security. We have seen the effect of out of order executions, for example, when we discussed about the effect of cache memories, and then we discussed about the DRAMs with appropriate refresh, for example, as an important design criteria. So, we saw attacks targeting the cache, the branch predictions, the DRAM, and more attacks are emerging as we are discussing, and security is getting to be a game changer, and therefore, design for security along with other objectives like performance, power, energy seems to be very important. And I would also like to make a comment here that it seems like the von Neumann architecture is due retirement. It seems to be fundamentally insecure, and it is a good time to think of a clean paper design of a computer architecture. So, RISC-V is a good open source platform to experiment, and we can actually potentially do several investigations and maybe like kind of do investigations about various and try to think about a clean slate design of with security as an upfront design criteria. So, just to quote like for example, the famous Hennessy-Patterson in this context. So, in this discussion on viewpoint published in Communications of ACM, there was an interesting comment which says that the other thing which we essentially are getting better at is, or which we need to get better at, is security. So far we haven't asked much of computer hardware in security, and I think that architects need to step up and really help attack this problem. And he says that what is exciting is that RISC-V is something which is essentially available open source, and which we can potentially try to investigate to develop an implementation or a processor architecture with security as an inbuilt design criteria. So, with this, this is a reference that you can follow for our discussions on row hammers. So, this is the book which is published by Springer, and you can get also an access to this work and several references which has been mentioned in this work. So, with this I would like to say thank you to you for your attention. Thanks.